At first glance, the idea of charging a vehicle at 1.2 megawatts borders on the absurd. For most Americans familiar with electric cars, even the fastest charging numbers still live in the hundreds of kilowatts. A typical Tesla supercharger today peaks at around 250 kilowatt-hour, while newer high-power stations push 350 kilowatt under ideal conditions. Against that backdrop, 1.2 megawatt feels less like incremental progress and more like a fundamental break from reality. But engineering is never about isolated numbers. Context matters, and once you step back and examine the global landscape, the vehicle class involved, and the infrastructure constraints unique to the United States, Tesla's demonstration becomes far more than a publicity stunt. It becomes a meaningful signal that electric long-haul trucking has crossed a technical threshold many assumed was still a decade away. Globally, megawatt-scale charging is not entirely unprecedented. China, driven by centralized planning and aggressive electrification policy, has advanced high-voltage charging infrastructure at a remarkable pace. Certain premium passenger EVs there already approach comparable peak power levels under controlled conditions. The crucial distinction, however, is not the vehicle itself. It is the system supporting it. In the US, ultra-high power charging remains fragmented, rare, and often constrained by local grid limitations. Delivering 1.2 megawatt repeatedly and reliably on American freight routes is not merely a battery or motor challenge. It is a systems-level accomplishment involving power electronics, grid coordination, thermal management, and industrial-grade safety margins. That is precisely why the Tesla Semi deserves serious attention. The Tesla Semi is not an oversized passenger EV. Estimates place its battery capacity between 800 and 900 kilowatt-hours, roughly 10 times larger than the battery pack in a typical electric sedan. When Tesla previously stated that the Semi could recharge 70% in 30 minutes, many industry veterans were understandably skeptical. The arithmetic is unforgiving. To push roughly 600 kilowatt-hour into a battery in half an hour requires sustained power well above 1 megawatt. No existing supercharger network, even Tesla's own, could support that. Until now, such claims lived mostly on presentation slides. The 1.2 megawatt test changes that. It demonstrates that Tesla is not theorizing in isolation, but actively validating megawatt charging with real trucks on real American routes. That distinction matters. Fleet operators, unlike consumer buyers, care less about marketing claims and more about repeatability, uptime, and total cost of ownership. Major early customers such as PepsiCo have already deployed semi-trucks in daily service, reporting real-world ranges approaching 500 miles. That alone suggests Tesla has quietly resolved several issues: battery durability, thermal stability, drivetrain efficiency. That stalled earlier electric truck programs. Still, raw charging power is only one piece of the puzzle. Reaching 1.2 megawatt is an achievement, but it also exposes serious technical risks that cannot be ignored. First, heat. At megawatt-scale currents, even minimal electrical resistance produces extraordinary thermal loads. Without aggressive cooling, connectors, cables, and internal contacts would degrade rapidly or fail outright. Tesla's approach relies on liquid-cooled cables and immersion-cooled connectors, where coolant circulates directly around critical components. At this level, such systems are not optional add-ons. They are structural necessities. It also underscores an important safety point. Improvised cooling tricks sometimes seen among consumer EV users, such as wrapping wet cloths around charging handles, are not merely ineffective at megawatt levels. They are dangerous. Megawatt chargers depend on precise thermal sensors and automated shutdown logic. Interfering with those systems could result in catastrophic failure. Second, battery longevity. Charging an 850 kilowatt-hour battery at 1.2 megawatt corresponds to roughly a 1.4 C charge rate. While not extreme by passenger EV standards, it is significant for a heavy-duty truck expected to operate daily for hundreds of thousands, if not millions, of miles. Repeated high-power charging stresses cell chemistry, current collectors, and thermal interfaces. Tesla's confidence rests largely on its 4680 cell architecture, designed to handle high current densities while maintaining structural rigidity and cooling efficiency. Third, grid impact. A single Semi charging at 1.2 megawatts draws as much power as a small residential neighborhood, Multiply that by several trucks charging simultaneously, and local distribution infrastructure quickly becomes a bottleneck. Voltage sag, transformer overload, and punitive peak demand charges are not theoretical concerns. They are immediate operational realities. This is why serious deployments pair megawatt chargers with on-site battery storage, such as Tesla Megapacks. These systems buffer grid demand, smooth load spikes, and reduce energy costs through peak shaving. Without them, large-scale electric trucking simply does not pencil out. Early semi-prototypes relied on modified proprietary connectors. That approach was never sustainable. Tesla's decision to adopt the Megawatt Charging System (MCS) standard marks a pivotal shift toward industrial maturity. MCS offers higher current tolerance, improved thermal stability, robust physical locking, and, critically, cross-manufacturer compatibility. This means future semi-trucks will not be locked into Tesla-only infrastructure. They will be able to charge at standardized heavy-duty stations shared across the industry. For fleet buyers, that reduces risk. For regulators, it improves safety. And for the broader market, it accelerates adoption by preventing fragmentation. It is essential to understand that 1.2 megawatt represents peak power, not a constant rate. Like all batteries, the Semi follows a charging curve. Maximum power is delivered at lower states of charge, typically below 30 to 50%, then tapers to protect cell health. To achieve Tesla's claimed 70% charge in 30 minutes, the system must maintain an unusually flat and stable charging curve at extremely high power levels. Early test results suggest this is achievable. But scaling that performance across thousands of trucks, climates, and duty cycles remains the true test. Here is where Tesla's strategy reveals its practicality. A Semi consuming roughly 1.5 kilowatt-hour per mile with an 850 kilowatt-hour battery delivers about 500 miles of range. Charging from 10 to 80% at megawatt speeds takes approximately 30 minutes, almost perfectly aligned with mandated driver rest periods. That alignment is not accidental. Diesel trucks may refuel in 15 minutes, but they stop more often and incur higher maintenance downtime. Electric trucks trade fewer stops for longer, regulation-compliant brakes, turning required rest into productive charging time. How has the Tesla Semi been refreshed to mass production in 2026? When 2026 opened, Elon Musk set the tone with a simple promise. 2026 will be a banger. For longtime observers of Tesla, especially those who have followed the company's ambitions in heavy-duty trucking, that statement immediately carried weight. Within days, the promise took physical form. After nearly 8 years of waiting, the Tesla Semi finally reappeared at Giga, Nevada. Not as a prototype, not as a teaser image on a presentation slide, but as a real, refreshed, production-intent vehicle. This was the Semi Gen 2, and its arrival quietly answered a question many in American trucking, logistics, and manufacturing have been asking for years. How did Tesla rework the Semi to make true mass production in 2026 possible? The answer lies not in one dramatic breakthrough, but in a disciplined, industrial refresh, an approach that should feel familiar and reassuring to anyone who values durability, efficiency, and long-term return on investment. The Tesla Semi has always been built around Giga, Nevada, a facility that has grown into the backbone of Tesla's American manufacturing system. This factory produces drive units, battery packs, and energy products, and it played a decisive role in scaling the Model 3 and Model Y. By the end of 2026, Giga, Nevada crossed an important milestone: 6 million drive units produced. Elon Musk publicly credited the factory team for that achievement, underscoring something important. Tesla did not gamble on the Semi. It waited until its industrial foundation was mature enough to support it. The updated exterior, first spotted by longtime Semi-watcher Zangler through drone footage, revealed a truck that looks familiar yet clearly evolved. The most obvious change is the new front light bar, similar in design language to the Model Y but scaled appropriately for a Class 8 truck. This is not cosmetic indulgence. Lighting design affects aerodynamics, manufacturability, and parts commonality across vehicles. Compared to the earlier headlight layout, this new design simplifies the front end while aligning the Semi with Tesla's broader production ecosystem, an important step when preparing for volume manufacturing. Efficiency is the defining theme of the Semi Gen 2. Tesla reports energy consumption of just 1.7 kilowatt-hour per mile, a roughly 15% improvement over earlier versions. For long-haul trucking, that number is not an engineering curiosity. It is the difference between a technology experiment and a viable business tool. Over hundreds of thousands of miles, a 15% efficiency gain translates directly into lower electricity costs, fewer charging stops, and higher asset utilization. Fleet managers understand this arithmetic instinctively. That efficiency gain did not come from one change alone. It is the cumulative result of improvements in aerodynamics, drivetrain optimization, software control, and, most importantly, the battery. Early semi-prototypes relied on LFP battery chemistry. LFP is safe and relatively inexpensive, but it comes with a drawback that matters deeply in trucking: low energy density. To reach a 500-mile range, LFP requires more cells, more mass, and more cost in the form of lost payload capacity. In freight hauling, weight is money. Tesla's decision to move the Semi to high-voltage 4680 battery cells marks a turning point. With energy density close to 300 watt-hour per kilogram, nearly double that of LFP, Tesla can achieve the same range with fewer cells and significantly less weight. The result is a tractor that carries more cargo without increasing gross weight, while also reducing manufacturing complexity. This single decision aligns perfectly with Tesla's stated goal of mass production in 2026. Fewer parts, lighter systems, lower cost per unit. Crucially, Tesla did not chase unrealistic range numbers. The refreshed Semi retains a 500-mile range, not because Tesla could not go further, but because it chose not to. By keeping the range constant while improving efficiency and battery density, Tesla reduced pack size, vehicle weight, and cost. This is an engineering choice rooted in commercial reality, not marketing. That same realism is evident in the Semi's charging system. Official footage shows the truck reaching a peak charging rate of 1.2 megawatts at a Tesla megacharger. This is unprecedented in the electric truck world. For American truckers, especially those accustomed to diesel refueling schedules, charging time is often the decisive objection to electrification. Tesla addressed that objection directly. At 1.2 megawatts, the Semi can recover hundreds of kilowatt-hours during a federally mandated rest break. In practical terms, this means an electric Semi can operate on duty cycles that closely resemble those of diesel trucks. Instead of carrying an oversized battery to last an entire day, the truck relies on fast, predictable charging. This reduces weight, increases payload, and improves profitability. Three priorities that resonate strongly with experienced operators. Power delivery has also been refined. The refreshed Semi is rated at 800 kilowatt, or roughly 1,070 horsepower, but raw horsepower numbers miss the point. Electric powertrains deliver torque instantly and smoothly, without the narrow RPM bands of diesel engines. For a fully loaded Class 8 truck, this means steady speed on long grades, confident merging, and less mechanical stress over time. More power combined with better efficiency is not a trade-off. It is a statement that electric drivetrains have reached industrial maturity. Some of the changes are smaller but no less telling. The side windows now end earlier, simplifying the cab structure and likely improving aerodynamics and manufacturing efficiency. Diamond plate anti-slip steps have been added to improve driver safety, a practical old-school consideration that signals Tesla's growing attention to day-to-day usability. A new camera placement near the front wheel hints at autonomy readiness, positioning the Semi for future deployment of advanced driver assistance, and, eventually, full autonomy on long-haul routes. All of these updates point to the same conclusion. The Semi has been refreshed not to impress on a stage, but to survive in a fleet. That conclusion is reinforced by real-world validation. DHL's trial of the Tesla Semi covered 3,000 miles over 2 weeks, hauling full loads at a gross combined weight of 75,000 pounds. The results were unambiguous: an average consumption of 1.72 kilowatt-hour per mile, an average speed above 50 miles per hour, and a single charge range of 390 miles under load. DHL estimates emissions reductions of 50 tons per truck per year, but just as importantly, it sees a clear economic case. As a result, DHL has confirmed plans to order more than just a handful of trucks. Tesla's broader manufacturing success provides important context. The Model Y has become the world's best-selling car for 3 consecutive years, outperforming long-established competitors through a combination of value, safety, and manufacturing efficiency. The same production philosophy, relentless simplification, vertical integration, and scale, now underpins the Semi. At the same time, Tesla is preparing its next wave of manufacturing innovation with the Cybercab, a vehicle designed to be produced more like consumer electronics than traditional automobiles. While separate from the Semi program, it demonstrates Tesla's confidence in high-speed, high-automation production lines, experience that directly benefits semi-manufacturing. Internationally, Tesla's steady expansion at Giga Berlin, even amid a challenging European market, further shows the company's long-term commitment to industrial stability rather than short-term reactions. Jobs preserved, infrastructure expanded, and capacity prepared. These are not the actions of a company unsure of its future. As Tesla looks toward 2026, the company is pressing ahead with long-term expansion plans in Europe, with Giga Berlin positioned at the heart of that strategy, even as the regional EV market remains under pressure. The European market proved challenging in 2025, particularly in Germany, where demand for electric vehicles softened sharply and Tesla registrations dropped by nearly half. Rather than retreating in response to these headwinds, Tesla has opted to strengthen its manufacturing base and focus on future growth. In an interview with German news agency dpa, Giga Berlin plant manager André Thierig confirmed that the factory has remained stable over the past year, with no layoffs and no production shutdowns. At a time when many German industrial facilities have been forced to reduce staff or halt operations, Giga Berlin has stood out as an exception. Thierig stressed that job security and uninterrupted production continue to be core priorities for Tesla at the site. So, with repeated megawatt-level charging, will battery degradation undermine the long-term economics of the Tesla Semi, or has Tesla's 4680 technology genuinely solved this risk? Please share your opinion in the comments section below this video. Thanks for watching our video. Subscribe now so you don't miss the next breaking Tesla update. It's coming in just 2 days. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Also, make sure to turn on notifications so you never miss our latest videos. We appreciate your support and look forward to seeing you in the next video.
Now this battery brings in our latest and greatest in terms of technology. It is cheaper to manufacture, and the best part is that it's actually less battery energy than in our current pilot production vehicles. But it maintains the same range. This is achieved through efficiency improvements that we're showing here, more than 7% at this point.
Tesla Semi is entering a critical transition phase, moving from limited pilot production to full-scale mass production. After 8 years of development, the company plans to begin online production at the Giga Nevada factory in the first quarter 2026, aiming to achieve real output, targeting 50,000 vehicles per year, equivalent to just over 4,000 vehicles per month, once the 1.7 million square foot Tesla Semi facility is fully operational. For the first time, Tesla will employ the massive GigaPress for the Semi line. This technology allows the production of large chassis components in just a few minutes, significantly accelerating manufacturing speed, with a goal of rolling out 1 truck every few minutes. Particularly the transition to next-generation 4680 cells, promising a 20% reduction in battery weight while maintaining a 500-mile range. Real-world production data from DHL and ArcBest show an energy efficiency of 1.55 kilowatt-hour per mile under full load, confirming the vehicle's practical potential to compete directly with diesel trucks on economic performance metrics. In today's episode, we'll explore 4 key topics: the detailed Tesla Semi production schedule for 2026, the evolution of battery technology from LFP to the latest 4680 cells used in the Tesla Semi Gen 2, the design upgrades in the Gen 2 Tesla Semi, and how partners like DHL and ArcBest have verified the energy efficiency achieved by the Tesla Semi under real-world operating conditions. Welcome to Tesla Car World. By the way, we've just updated the latest information on Tesla Semi's pricing policy for 2026. Honestly, it's truly different and has sent shockwaves through the heavy-duty electric truck market when compared to the Freightliner e-Cascadia or Volvo VNR Electric. If you want us to dive deeper into this gap, hit the like button to let us know so we can continue researching it in more detail. Thank you. Back to today's topic. What does the detailed Tesla semi-production schedule for 2026 look like? Tesla's updated production roadmap for the Semi in 2026 is far more credible than its earlier timelines because, for the first time, it is underpinned by visible construction progress, committed capital, and a maturing battery supply chain rather than slide deck promises. According to Tesla's the third quarter 2025 updates, the company expects the first online builds from its new dedicated semi-factory in Nevada to roll off the line in the first quarter 2026, with a structured ramp through the second quarter and true volume production in the second half of 2026, targeting an annualized rate of 50,000 units. This sequence, pilot builds, controlled ramp, then volume, is consistent with how Tesla has scaled previous platforms such as the Model 3 and Model Y, where early quarters focused on learning and debugging the line before throughput rose sharply. The fact that Tesla is explicitly distinguishing between online builds and real production suggests a disciplined, automotive-grade industrialization path rather than a marketing-driven announcement. The 2026 Tesla semi-production schedule is backed by tangible progress and major investments already in place. Tesla's 1.5 million square foot semi-facility at Giga, Nevada is essentially complete, with equipment installation underway, as confirmed in May 2025. Part of a $3.6 billion investment, the site includes a dedicated 100 gigawatt-hour 4680 battery plant to secure cell supply, previously the program's main bottleneck. This marks a shift from years of delays since the Semi's 2017 debut, during which only about 300 units were built. Unlike earlier low-volume validation runs, Tesla now has a dedicated factory, secured batteries, and clear executive commitment to scaling production. Furthermore, the 50,000 units per year target in the second half of 2026, while ambitious, aligns with the scale of demand and regulatory pressure facing the heavy-duty trucking market. Major fleets in North America, including PepsiCo, Walmart, and UPS, have placed reservations or expressed interest in zero-emission Class 8 trucks to meet corporate decarbonization targets and comply with increasingly stringent state-level rules, such as California's Advanced Clean Trucks and Advanced Clean Fleets regulations. These policies will gradually force a shift away from diesel, creating a structural incentive for manufacturers that can deliver electric trucks at scale. So how does the transition from LFP to 4680 batteries transform the Tesla Semi Gen 2? Tesla's evolving battery strategy for the Semi directly underpins the credibility of its 2026 mass production plan, because it shows a clear transition from constrained multi-supplier pilot chemistry to a unified vertically integrated 4680 platform sized for heavy-duty use. From 2022 to 2025, Tesla effectively treated the Semi as a low-volume, semi-experimental program, splitting chemistries by use case. Lithium iron phosphate packs of around 500 kilowatt-hour for the shorter-range 300-mile variant and higher-energy nickel-based chemistries in the 800 to 900 kilowatt-hour range for the 500-mile version. This dual approach allowed Tesla to validate real-world duty cycles and degradation profiles in different segments of the trucking market. LFP offered high cycle life, often quoted in the 2,000-plus full cycles range, and excellent cost and safety characteristics, which is ideal for regional haul operators who run trucks intensively and can live with slightly lower energy density. The NCA and NCM option, with typical cycle life on the order of 800 to 1,500 cycles, traded some longevity for the high specific energy needed to hit a 500-mile range without pushing the tractor's weight over regulatory or payload penalizing thresholds. The pivot in 2026 to high-voltage 4680 cells as the production-ready standard therefore represents more than a simple cell format change. Tesla reports that its 4680 HV architecture for the Semi improves energy efficiency by about 7%, allowing the truck to maintain a 500-mile range while shrinking total pack capacity. In practical terms, higher volumetric and gravimetric energy density translates into hundreds of kilograms, potentially over 1,000 pounds, removed from the pack relative to earlier NCA-based designs. That weight reduction contributes directly to a lower curb weight, with internal targets and external analyses converging around a sub-23,000-pound figure for the tractor, versus previous estimates in the 24,000 to 26,000-pound range. Every pound shaved off the tractor's mass can be reallocated to payload within the 80,000-pound U.S. gross vehicle weight limit, an advantage that fleet operators can monetize immediately in the form of additional freight per trip. How impressive are the Gen 2 upgrades for the 2026 Tesla Semi? Tesla's second-generation Semi design, unveiled at the 2025 annual shareholder meeting, is best understood as a deliberate shift from engineering prototype to a platform optimized for high-volume manufacturing and long-term autonomy. The front fascia now borrows LED headlamp modules from the Model Y and Cybertruck, a choice that is not just aesthetic but economic. Reusing proven lighting assemblies cuts tooling costs, simplifies supply chains, and ensures regulatory compliance in multiple markets. At the same time, Tesla has reduced the windshield's overall area, trimming glass weight while improving aerodynamics. A smaller, more steeply raked windshield reduces frontal drag and can lower cabin cooling loads, which marginally improves real-world efficiency, small gains that compound over millions of fleet miles. The softer, more conventional roofline ties into this aerodynamic strategy. Compared to the sharply faceted prototype shown in 2017, the updated cab profile appears tuned for manufacturability, simpler stampings and fewer compound curves, and for laminar airflow at highway speeds. Beneath the surface, the redesigned chassis is the core of the Gen 2 story. Tesla now targets a curb weight below 23,000 pounds, a meaningful improvement over earlier estimates of 24,000 to 26,000 pounds for the first-generation trucks. For freight operators constrained by the 80,000-pound U.S. gross vehicle weight limit, each ton of tractor weight eliminated is a ton that can be reassigned to payload, directly impacting revenue per trip. Achieving this weight reduction while maintaining a 500-mile range strongly implies deeper integration of the 4680 HV pack structure into the frame, greater use of high-strength steels or alloy stampings, and a more modular underbody designed for automated assembly. Tesla's broader manufacturing playbook, gigacastings, structural battery packs, and highly integrated wiring harnesses, is likely being applied here, even if the company has not disclosed every specific technique, because those are precisely the levers it has used to reduce cost and complexity in its passenger vehicles. A major visible evolution in the Gen 2 Semi is its sensor suite and overall autonomy architecture. Tesla now describes a layout with more than 26 cameras, including units mounted around the front arches and high on the cab, to provide overlapping 360-degree coverage with redundancy in critical zones like blind spots, trailer edges, and merging lanes. This configuration is tailored to the operational realities of Class 8 trucking, long trailers that articulate, tight depot maneuvering, and continuous highway operation where lane changes and merges are frequent. By designing the cab structure, fairings, and mounting points around this dense camera array from the outset, Tesla avoids the compromises and serviceability issues that can arise when autonomy hardware is retrofitted. The electronic and control architecture has reportedly been simplified as well, fewer ECUs, more centralized compute, mirroring Tesla's shift in passenger vehicles to a single powerful FSD computer that handles both driving and many body control functions. That consolidation reduces wiring, cuts points of failure, and improves over-the-air update capability, all key for fleets that demand uptime and predictable maintenance. Aerodynamics remain central to the Semi's economics, and Tesla's Gen 2 updates appear to refine, rather than radically alter, the original strategy. The company continues to cite an energy consumption figure of about 1.7 kilowatt-hour per mile for the long-range variant, suggesting that, while the coefficient of drag may have improved, Tesla is framing those gains as a margin of safety or headroom rather than revising public claims upward. Any drag reduction beyond the already competitive initial design could translate into higher effective range under real-world conditions, or allow Tesla to downsize the pack slightly without sacrificing the headline 500-mile capability. In practice, fleets care much about consistency, achieving that range in varying weather with different trailer shapes and loads as about the absolute best-case number. Incremental aerodynamic refinements in the cab, fairings, mirror camera pods, and tractor-trailer gap management are likely aimed at tightening that variance band so that route planning and charging schedules can be made more reliable. One of the most strategically important Gen 2 upgrades is the introduction of an electric power takeoff system. Traditionally, refrigerated trailers and other auxiliary equipment rely on separate diesel engines to power their compressors or pumps, adding fuel costs, maintenance complexity, and local emissions even when the truck itself is not moving. Tesla's ePTO, rated up to roughly 25 kilowatts, allows the Semi to supply this power directly from its traction battery, effectively electrifying the entire truck-trailer system. This architecture can eliminate a significant source of idling diesel consumption and noise in logistics hubs, ports, and urban delivery zones, while also simplifying compliance with tightening anti-idling and emissions regulations. Because Tesla controls both the vehicle and the high-voltage power architecture, it can integrate ePTO management into the same software stack that optimizes traction, regen, and charging, ensuring that auxiliary loads are scheduled intelligently so they do not compromise mission-critical range. The Gen 2 design's explicit focus on full self-driving readiness also positions the Semi for a longer technology runway than many competing electric trucks. By hardwiring in substantial sensor redundancy, centralized compute, and a body layout that assumes autonomy hardware will be standard rather than optional, Tesla is effectively front-loading the capital needed for a truck that can evolve via software. In the near term, this means advanced driver assistance features, automatic lane keeping, adaptive cruise, and supervised highway driving that reduce driver fatigue and improve safety. Over time, if Tesla succeeds in extending its FSD capabilities to commercial freight corridors, the same hardware could support more automated operation on dedicated lanes or hub-to-hub routes, where the economics of driver time and utilization are most sensitive. For fleet buyers making 10 to 15-year asset decisions, that embedded autonomy roadmap can be as important as the current spec sheet, because it defines how the truck's earning power might improve over its service life. How have partners like DHL and ArcBest validated the Tesla Semi's energy efficiency under real-world operating conditions? Tesla's early customer base for the Semi provides some of the strongest real-world validation that the product is economically and operationally viable at scale, despite a still limited production run. PepsiCo, Tesla's launch partner, has accumulated more than 7.5 million kilometers of operation since 2022, a mileage figure comparable to what a medium-sized regional fleet might log across several diesel tractors over multiple years. Over that distance, Pepsi's reported energy consumption has not only met, but in many cases beaten Tesla's 1.7 kilowatt-hour per mile target, indicating that the efficiency claims from the 2017 reveal are holding up under routine, loaded operation. Pepsi's demonstration of a roughly 1,050-mile 24-hour duty cycle using Tesla's Megawatt Charger infrastructure is especially important. It proves that the combination of battery capacity, charge rate, and driver scheduling can support high-utilization freight operations rather than just short, publicity-focused runs. New entrants like DHL further corroborate those performance numbers. After a successful trial, DHL took delivery of its first Semi in December 2025 and reported around 1.72 kilowatt-hour per mile when hauling 75,000 pounds, very close to gross vehicle weight limits and therefore representative of real freight duty. DHL has already signaled that it intends to deploy more than just a handful of units in 2026, and it estimates about 50 metric tons of CO2 emissions avoided per truck per year compared with a modern diesel. For a global logistics provider that reports its emissions to investors and regulators, that kind of per-vehicle impact is material. ArcBest's 3-week trial in July 2025 adds another data point. Over 4,494 miles, the company recorded an even lower average of 1.55 kilowatt-hour per mile, while praising the Semi's ease of use, driver visibility, and comfort. These qualitative factors matter because driver recruitment and retention are major pain points in trucking. A vehicle that is more pleasant and less fatiguing to operate can indirectly reduce labor costs and downtime. Interest from large retailers such as Walmart, Costco, and Cisco, reported as upcoming customers, suggests that the Semi is not a niche experiment confined to a few green-minded brands, but a product being evaluated by some of the largest shippers in North America. These companies operate huge, time-sensitive logistics networks and tend to be conservative about deploying unproven technology. Their willingness to place or consider orders indicates that the Semi's real-world data, particularly from PepsiCo and early freight pilots, has crossed an internal credibility threshold. At the same time, the experience of Ryder Systems highlights the key tension around price. Ryder initially ordered 42 Semis but later cut that to 18, citing significant price increases and changing product economics, and now expects final deliveries around June 20, 2026. Industry analysis suggests that while Tesla originally floated a $180,000 USD price for the 500-mile variant in 2017, Actual transaction prices may now be in the $250,000 to $400,000 USD range, depending on configuration and battery size. This upward drift in capital cost does not necessarily undermine the business case, because the semi's economic strength lies in substantially lower energy and maintenance costs. At a consumption rate of 1.7 kilowatt-hour per mile and an industrial DC charging price of $0.20 US per kilowatt-hour, a reasonable US average for large commercial customers, a semi's energy cost is about $0.34 US per mile. A comparable diesel truck achieving 7 miles per gallon at $4.50 per gallon of fuel incurs roughly $0.64 per mile in fuel cost. The $0.30 per mile spread translates into about $30,000 in annual savings at 100,000 miles per year. So, has Tesla's shift to 4680 batteries genuinely solved the cost and weight problem for electric Class 8 trucks, or has it simply shifted the risk to long-term durability and replacement costs? Please share your opinion in the comments section below this video. Thanks for watching our video. Subscribe now so you don't miss the next breaking Tesla update. It's coming in just 2 days. If you want to explore more exciting information about Tesla EV or Tesla Bot, don't forget to hit the like button and share this video. Also, make sure to turn on notifications so you never miss our latest videos. For more than a decade, humanoid robots have been putting on impressive demonstrations, running, jumping, and moving in ways that look almost human. But none of that answers the only question that actually matters. Can any of these machines work safely, reliably, day after day, next to real people in the real world? As we move into 2026, the Tesla Bot Gen 3 is expected to go on sale officially, marking Tesla's entry into a field already shaped by established players such as Boston Dynamics, Hyundai, and Chinese competitors including Unitree and Agabot. The key issue lies in cost. With an anticipated price of around $20,000 per Gen 3 unit, this remains a significant barrier, especially when Unitree is already offering models like the R1 and H1 at prices ranging from $6,000 to $14,000. So the issue is no longer which robot is the most advanced. The issue is which one is actually ready for deployment and which ones are not. We are asking, which of these humanoid robots is truly ready to operate safely, reliably, and at scale in the real world? Before diving into specifications or performance claims, there is a critical step that must be clarified. In discussions about humanoid robots, 3 concepts are often blurred together: technical demonstrations, controlled testing, and real-world deployment. Without clearly separating these 3 layers, any comparison becomes vague and misleading. For that reason, to evaluate Tesla Bot Gen 3 fairly, we need a simple yet practical analytical framework. So, for the next few minutes, we'll begin with a simple framework, one that avoids hype and focuses on what truly matters beyond the laboratory. Once that foundation is clear, the comparisons will make far more sense. If you are interested in how humanoid robots are evaluated not by impressive video clips, but by their ability to endure and function over the long term in real-world environments, then the analysis that follows will continue along this same line of thinking. We will be tracking the subject over the long term, as real-world data and actual deployments gradually emerge. Humanoid robots, in reality, are not a new concept. For more than a decade, we have witnessed remarkable technical demonstrations, robots running, jumping, maintaining balance, and even performing complex movements. But demonstration is not the same as deployment. A robot may perform flawlessly in a carefully staged demo, yet that tells us very little about its ability to work day after day in unpredictable conditions. The greatest challenge has never been whether robots can move like humans. The real challenge is whether they can perform repetitive tasks over long periods of time with a level of safety high enough that people are willing to stand beside them. That gap is precisely where Tesla Bot Gen 3 claims it is moving closer than previous generations. However, Tesla is not entering this arena alone. Boston Dynamics, with its Atlas robot, has long been regarded as the benchmark for humanoid mobility. Hyundai, through its investments in robotics development, approaches the problem from a more industrial perspective, closely tied to logistics and factory environments. What we therefore need to compare are not promises, but the design philosophies and deployment paths each player is pursuing. Tesla Bot Gen 3 is no longer discussed as a standalone concept. It now appears in the same conversation as Boston Dynamics' Atlas and Hyundai's humanoid robotics programs. And notably, the central question has shifted. It is no longer about which robot looks more impressive, or which one moves with the greatest agility. The real question is this: which of these machines is truly ready to work safely, consistently, and over the long term in the real world? At this point, many people assume that the robot with the most impressive movement is the one closest to deployment. In practice, that assumption is usually wrong. When it comes to safety and control, the differences between these robots begin to stand out clearly. Boston Dynamics' Atlas demonstrates movements that are undeniably impressive and, at times, almost theatrical. Yet those movements take place in carefully prepared environments. The real world does not run on a script. Floors are uneven, people move unpredictably, and unexpected situations are unavoidable. Tesla Bot Gen 3 appears to be taking the opposite approach. Rather than maximizing speed or agility, Tesla emphasizes slow, controlled motion, relying heavily on vision systems and cognitive software. This suggests that Tesla is prioritizing safe interaction with humans over visually stunning demonstrations. Hyundai is pursuing a similar path, limiting its robots to well-structured industrial spaces where risks can be managed more effectively. What is crucial to understand is that safety in robotics is not about how many things a robot can do, but about what it is deliberately designed not to do. A machine that understands its own limits is always more reliable than one that constantly tries to push beyond them. When we turn to the second factor, energy efficiency and operating cost, the comparison becomes even more grounded in reality. A humanoid robot does not need to be the strongest, it needs to be economical. If a robot can only operate for short periods before requiring recharging, maintenance, or human intervention, it cannot yet be considered a true worker. Tesla holds a clear advantage in batteries, electric motors, and energy management, areas that have been thoroughly proven in the electric vehicle industry. Atlas, despite its exceptional mobility, has historically required high levels of energy and maintenance. Hyundai, with its industrial orientation, appears to place greater emphasis on continuous uptime and cost per working hour. Metrics that may be unexciting on a demonstration stage, but ultimately determine success or failure in real-world deployment. So the real question becomes this: would you rather deploy a robot that can perform spectacular movements for 20 minutes, or one that can work quietly for 8 hours with minimal supervision? Finally, there is the factor many companies prefer not to address directly: the deployment roadmap. Announcing a robot is one thing. Deploying thousands of robots in real environments is an entirely different challenge. Boston Dynamics possesses world-class engineering capability, yet large-scale commercialization of humanoid robots remains limited. Hyundai is moving forward cautiously, integrating robots into its existing industrial ecosystem. Tesla, by contrast, is presenting a more ambitious vision, leveraging its manufacturing capacity, software expertise, and supply chain to aim for deployment at scale. At this point, however, a fair evaluation requires addressing an issue that is rarely discussed in promotional material, yet increasingly difficult to ignore. In recent months, questions have emerged not about Tesla Bot's hardware, but about the ownership and control of its intelligence. As of early 2026, multiple reports indicate that xAI, Elon Musk's separate artificial intelligence company, is playing a direct role in developing the cognitive software that powers Optimus, rather than this work being handled entirely within Tesla. On a technical level, this may appear logical. From a legal and organizational perspective, however, it introduces a more complex set of considerations. Tesla is a publicly traded company. xAI is a private one. Several Tesla shareholders have raised concerns, now moving through legal channels, that intellectual property, engineering talent, and strategic focus may be shifting from Tesla toward xAI. The core question is not whether xAI is capable of building advanced AI systems. It is whether Tesla ultimately retains control over the brain of its humanoid robots. If the intelligence that enables perception, decision-making, and learning resides primarily with xAI, Tesla risks becoming, in functional terms, a manufacturer of frames, actuators, and motors, while the most valuable layer of the system lives elsewhere. This distinction matters, especially in the context of large-scale deployment. In robotics, long-term value is rarely created by hardware alone. It emerges from the tight integration of software, data, and continuous improvement over time. To be clear, this does not invalidate Tesla Bot Gen 3 as a deployment candidate. But it does introduce a structural uncertainty that deserves attention, particularly for those evaluating Tesla not merely as a robotics manufacturer, but as an AI company. Whether this division ultimately strengthens or weakens Tesla's position will depend on how ownership, licensing, and control are resolved in practice. For now, it remains an open question, one that sits at the intersection of technology, governance, and long-term strategy. The pivotal question is not whether humanoid robots will be deployed. The real question is where they will be deployed, under what conditions, and with what limitations. With this analytical framework in place, Tesla Bot Gen 3 is no longer an abstract idea. It becomes a concrete candidate for specific, real-world use cases. This brings us to the question most companies tend to avoid answering directly. With this framework, we can now examine Tesla Bot Gen 3, not merely as a concept, but as a genuine contender for real-world deployment. In the next section, we will look at where Tesla Bot Gen 3 can realistically be used first, and, just as importantly, where it is clearly not yet ready. So how are humanoid robots actually ready to step into the real world? Once Tesla Bot Gen 3 is placed within the proper analytical framework, the next question is no longer what it might do in the distant future, but what it can do immediately under limited deployment. In technology, sustainable progress rarely begins with complex scenarios. It usually starts with simple, repetitive, low-risk tasks, jobs people perform out of necessity, not because they require creativity. The most realistic initial deployment scenario for Tesla Bot Gen 3 is likely to be in factory and warehouse environments. These settings are relatively structured, processes are standardized, and interactions are largely predictable. A humanoid robot does not need to be exceptionally fast or strong to create value. It needs to be stable enough to carry out tasks such as moving light objects, organizing components, or assisting with repetitive steps along a production line. In this context, the strength of Tesla Bot Gen 3 does not lie in raw mechanics alone, but in its ability to integrate with a broader software and data ecosystem. A robot that can see, recognize objects, and understand context does so not merely through sensors, but through machine learning models trained on vast amounts of data. Compared with Boston Dynamics Atlas, which stands out primarily for its mobility, Tesla Bot Gen 3 appears designed to become part of an operational process rather than a standalone performance. Hyundai, with its industrial focus, is targeting much the same territory, but in a more cautious manner. Its robotic systems tend to be tightly coupled with logistics and warehouse operations, where robots function as specialized tools. Tesla, by contrast, is pursuing flexibility, a robotic platform capable of learning multiple tasks within the same working environment. From the factory floor, the next logical use case is large-scale logistics and warehouse operations. These are environments where humans and machines have coexisted for many years, with well-defined safety standards. Tesla Bot Gen 3 does not need to fully replace human labor. It only needs to reduce the burden of highly repetitive tasks, such as short-distance item transport, assisting with packaging, or handling light goods. Here, the deciding factor is not complex mobility, but reliability over time. A robot that can work 8 hours a day with a low error rate delivers far more value than one with superior technical capabilities but high maintenance demands. In this comparison, Tesla's advantages in energy management and software become more apparent, while Atlas remains constrained by cost and operational complexity. Another use case often mentioned, but one that requires a more cautious approach, is assistance in commercial and service environments. Tasks such as basic cleaning, restocking shelves, or supporting staff during peak hours can be low-risk scenarios if deployed correctly. However, unlike factories, commercial settings involve more direct and unpredictable interaction with people. This demands a higher level of social awareness and responsiveness, areas in which current humanoid robots are still very much a work in progress. For these reasons, such applications are more likely to appear first as pilot programs, limited in scope and closely supervised, rather than as mass deployments. Tesla Bot Gen 3 would serve in a supporting role, not as a replacement, and would perform only tasks with clearly defined boundaries and behaviors. When it comes to healthcare or elder care, caution must be paramount. While the long-term potential is significant, especially in aging societies, this is not an area where Tesla Bot Gen 3 is ready for direct involvement. In the near term, any consideration should be limited to logistical support. transporting supplies, providing simple reminders, or assisting medical staff with non-clinical tasks. Compared with more science fiction-like claims, this pragmatic approach highlights an important reality. Humanoid robots should only be deployed where errors do not carry severe consequences. In this context, Tesla Bot Gen 3 has an advantage if it is positioned as a supportive tool rather than a replacement for human beings. By contrast, there are domains where Tesla Bot Gen 3 is clearly not suitable in the near future. Uncontrolled outdoor work, complex construction environments, or situations requiring subtle social judgment remain beyond the capabilities of today's humanoid robots. In these areas, Boston Dynamics Atlas, with its superior mobility, may be better suited for research or highly specialized applications, but even there, widespread deployment is still a long way off. What is important to emphasize is that progress in robotics does not happen in sudden leaps. It advances step by step, through specific, limited, and carefully controlled applications. If Tesla Bot Gen 3 is deployed successfully, it will most likely appear first in places that attract little attention. Not on a stage, but in the corners of factories, warehouses, and logistics centers. It is in these environments that the true value of humanoid robots is ultimately tested. Not by promises, but by the ability to work quietly, consistently, and reliably. And that, in the end, is the only measure that truly matters when judging whether Tesla Bot Gen 3 is bringing humanoid robots closer to everyday reality. How does Tesla actually solve these problems? Beyond hardware, software, and deployment logistics, there is another constraint that will quietly shape whether humanoid robots can operate at scale: accountability. Specifically, who is legally and operationally responsible when an autonomous humanoid system makes a decision that results in harm or operational disruption? This issue becomes more complex when the intelligence driving a robot is developed by a different entity than the one manufacturing and deploying the physical machine. Recent reports show that Tesla's Optimus relies heavily on xAI for its cognitive software. While this may accelerate AI development, it raises practical questions about certification and liability. In traditional industrial automation, responsibility is relatively clear. Consider KUKA's industrial robotic arms in automotive assembly lines. These machines are confined to fenced areas.